Okay, everyone, so welcome to our ninth lecture and our final topic of signal processing and circuits. Last week we finished about filters, and today we're going to start a completely new topic, which is the Fourier theory. We will cover this in 2 weeks, so this week and next week we'll be covering Fourier theory, and hopefully next week will be our last teaching session. After that, we will start with our revision sessions. So what are we going to cover today? Just in general. First, I'm going to explain to you what is the Fourier theory in general. Fourier theory applies to two different types of signals. So we're going to look at the two representations of Fourier theory. Namely, they are called the Fourier series and the Fourier transform. So we're going to look at the concept, the meaning, the application, and the equations and the equations of both applications, Fourier transform and Fourier series. Then we're going to have a few more in-depth examples about Fourier transform in today's class and some of the transform properties. So in today's class, we're going to look at Fourier theory in general with a focus on Fourier transform. Next week, we're going to look at the other half, which is the Fourier series. Clear? Huh? I'm just giving the brief يعني الأشياء اللي حنغطيها اليوم بنغطي موضوع جديد اللي هو الفورير ثيوري. فورير ثيوري فيها جزئين، الترانسفورم والسيريز. فاليوم هناخد الثيوري كجنرال what is the theory, what is the series, what is the transform، وهناخد أمثلة أكثر على الترانسفورم. الأسبوع الجاي بناخد أمثلة أكثر على الجزء الثاني اللي هو السيريز. وعليكم السلام. Revision is the week after next اللي هو first week of May. Okay? So let us start with the Fourier theory. What is the Fourier theory? Fourier is obviously a name of the scientist who came up with the theory. So the theory says that any continuous periodic signal could be represented as a sum of properly chosen sinusoidal waves. What does that mean? Let's look at the theory in more details. It says that any signal that satisfies two conditions. Number one, being continuous. Number two, being periodic. If a signal is continuous and periodic, then we can represent it as the sum of properly chosen sinusoidal waves. What does properly chosen mean? Now, when we study sinusoidal waveforms, sine and cosine, we said that what are the differentiating factors? Amplitude, frequency, phase shift, right? So Fourier theory says that if you choose sinusoidal waveforms with specific amplitudes, with specific frequencies, then add them all together, you can create the same signal as a continuous periodic signal, and we can apply that to anything. Now, these have to be harmonically related for the Fourier series, and they don't have to be harmonically related for the Fourier transform. What does that mean? First of all, if we look at the signal here, is this a series? Is this a, periodic continuous signal or no? The one at the bottom. Is it periodic? Is it continuous? Do we know what continuous means? Have a continuous value in time, which means this is continuous, but this is not, because in this area there is no value, right? So if it's continuous and periodic, then we can use the Fourier series. If it's continuous but aperiodic, we can use the transform. Both series and transform, what is the series and what is the transform? It's a combination of sinusoidal waveforms. Just to make it more clear, this is a visual example of what Fourier series is. If you look at this signal over here, the red signal, which is the train of pulses, this is a continuous periodic signal, correct? Okay. This signal can also be, signal y of t, could also be represented as the sum of these signals, y1 plus y2 plus y3 plus y4 onwards. What is y1, y2, y3? Sinusoidal signals, right? y1, for example, is 3 sine t, which we have over here. y2 is sine 3t. y3 is 0.8 sine 5t, and so on, right? If you look at it, when we add y1 to y2, this is what we have, which is a distorted version of the original signal, not the signal, just a distorted version of it. But when I add y3, I get closer to the original signal. When I add y4, I get even closer. Does that make sense? So therefore, if you add enough number of terms, you'll have the exact same original signal. Does that make sense? Why do I have to do this? Why do I have to represent a regular signal or a signal that is continuous and periodic with this sinusoidal representation? Now remember in the first class when I said that one of the most common used signals is the sine waveform, the sinusoid. In addition, a sine signal or a cosine signal can be represented as an exponential signal, right? We know the rule that sine x is equal to e power jx minus e power j minus x over 2j. Do you know that? Euler's identity. And cosine is equal to the same thing just without the j, right? So the sine wave on its own, and we studied that phasors come from sinusoidal waveforms, right, from the cosine. So if you have a signal that can be represented as a complex number that could be represented as an exponential, it makes it easier to manipulate it when we're doing circuit analysis, right? So rather than dealing with any shape, for example, this one, what does this signal look like? What is this signal? We don't know. We don't have a formula for it, right? But if I'm able to break it down into a series of sine waveforms and cosine waveforms, then I can mathematically represent it easier, and therefore I can manipulate it, I can evaluate it, I can test how it will result as an input to a system, and so on. Make sense? So the whole purpose of Fourier theory is simplify the way we review signals in order to mathematically manipulate them or analyze them in a circuit. Clear? So let's have another example. Let's go to this applet. Where is it here? If you look at this here, is it visible to you? Or it's better we turn off? Yes, please. Okay. So what I want you to do is focus on the white line signal. Over there, is it visible? شايفين؟ اوكي شايفين؟ بس ما تناموا. اجواء هادئه بقت. طيب شوف الوايت سيجنال، بس كذا وايت سيجنال. It's a sawtooth signal. Okay? If I want to represent this using Fourier theory, I have to find sinusoidal waveforms that I can add them to create this signal, right? So what we do is we add, for example, in our example here, we had 4 terms only, right? Let's close this. We had only 4 terms. But if I go back to the applet, let's add 1 term. That's the first term, the red sinusoidal waveform, right? With a specific amplitude and a specific frequency. And then if I add a second term, what will happen? Got a little closer, right? So if you look, this here is the first term, the yellow one. This is the second term. Let's add a third. This is the third term, this yellow one. And then the sum of all of them is the red line, right? And then I will just continue adding terms. What do you notice happens when I continue adding terms? The more terms I add, the closer you get to the original signal, right? Yes? At the same time, I want you to look at the terms themselves. This is number 1, the yellow one. This is 2. This is 3. This is 4. What do you notice is happening? 5, 6, as we progress in terms. The amplitude decreases, the frequency increases. So the first term has the most effect, right? Because it has the highest weight, the highest amplitude. And if you look at the first term here, it's a sine waveform, right? And this is a triangular waveform, right? The same thing can be done to any shape. It doesn't have to be a specific regular shape, even if it's irregular. It could be a triangle. And then I just add terms and I will get closer to the triangle, right? It could be some sort of noise. Now, obviously with noise, it's very difficult to get closer, but we'll try to get closer. But generally, if it's a regular repetitive waveform, it can be represented by a sum of um, sinusoidal waveforms, sine and cosine functions. Okay. So with that, let's go back to our slides. Just give me a moment. Okay, back to our notes. So therefore, Fourier theory says that you can take any function in any form as long as it's continuous and periodic. You can represent it by a sinusoidal series, and you'll notice that the frequency, the gain obviously changes, the amplitude, sorry, 3, 1.8.4, it's reducing this as it, and the frequency, omega, here it's 1, here it's 3, here it's 5, here it's 7, right? It's all a multiplication of 1, right? It depends. So that original frequency, omega naught, which in this case is equal to 1, is the frequency of this original signal. Clear? So we call these harmonically related because they have all of their frequencies are multipliers of a single base frequency. If the signal was aperiodic, which is this case, they don't have to be harmonically related. They will be just a completely different series. Clear? Up till this point, do I have a question? Okay, so what do we need to learn? In order to be able to use this theory, we need to know what is the rule. How do I calculate these harmonically related sinusoids? How do I calculate the magnitude? So basically, this is a general term, right? A of n sine omega n or omega naught t multiplied by n, right? This is basically what you have. A of n, for each term, you have a value of amplitude. For each term, you have a multiplier of a base frequency. Plus, sometimes you have a cosine also. So let's say this is B, this is A of n cosine n omega naught t. So this is basically the form. It's a combination of cosines and sines sometimes. Yes, time omega naught t. So what is omega naught? It's the same frequency of your original function. So basically, it will be a combination of sines and cosines. But you'll notice that it depends on the function, this combination. Now, do you remember when we first studied signals that I told you that signals can be categorized as even and odd? Do you remember that? Do you remember what is an even signal? Okay, let's quickly jog your memory. What is happening for me? Just give me a moment. Okay, hopefully. Okay. Okay. So this signal, which looks like this, is considered even. Because when you look at it, let's call it x of t, or this is t, x of t is equal to x of minus t, correct? And whatever is happening in the right side is mirrored in the left side, right? As if we have a mirror here in the y-axis, right? So we call this an even signal. And another example of an even signal is the cosine. The cosine is in fact an even signal, right? Then we have what we call the odd signal. Now the odd signal is also mirrored but with a different axis of symmetry. For example, this signal. If you look at it, it satisfies the condition that x of t is equal to minus x of minus t, where the axis of symmetry is horizontal. So as if everything happening at upper right side is reflected in the lower left side, right? So this is called an odd signal. Another example of an odd signal that is very familiar with all of you is sine, right? So here I've mentioned that any signal can be broken down into a combination of of sine and cosine, which is basically odd and even, right? But if the signal itself is purely odd, it means there are no cosine terms, right? For example, this sawtooth. Let's go back to our applet.
So, Victor, the difference between even and odd.
Mm,
The odd is coming in the negative side, and
yes,
the even it's coming to
left and right. Yes. Okay, so let's share this for those who are online as well. So if you go back to the examples in the applet, where is it? Okay. So if we go to the applet, this signal is even or odd?
odd.
Are you sure?
It's because
This here, this point here is the axis of symmetry.
even. So it's coming in. Yeah.
Are you sure?
Even. No.
This is your center point, your line.
Okay, then even.
It's even, right? So when I say this is an even signal, do you expect it to have sine and cosine harmonics or only cosines? Only cosine, right? Very good. So if you look, I'm adding terms and I'm getting closer, but if you look, all the terms I have are cosines. I'm adding cosines. What's happening? What did I do? Just a moment. I'm doing a triangle. So if you look, all of them are cosines. But if you look at the sine, zero. There's no sign because it's, while if I look at this one, the signal is what? Even or odd? Odd, right? So you'll notice the more terms I add, these are purely sine, while there are zero cosines. So this is very important thing to notice. Now today I'm not going to give you examples of the Fourier series. Next week we will have. But it's very important to notice because usually when you have to find these harmonics, it means you have to calculate the amplitude, you have to calculate the frequency. And the calculation includes using of some rules or laws. But just by looking at this signal, I know all of the cosines will be zero. So I don't have to calculate them. If you calculate them, which you can do using the formula, and the formula is mainly an integration process, you can do like 3-4 pages of calculations and you'll arrive at the final answer equals zero. Or you can save yourself time and say the signal is odd, therefore the cosine is zero. So it's very important to pay attention to these things, and you'll notice how important it is when we move on to the calculations and an examples bit. But up till this point, is it clear to us how signals can be deconstructed into a combination of sine and cosine? Okay. So now just give me a moment. Okay. And let us move. So this is the Fourier series. And then we have the rules for the Fourier series, which is how do you calculate these amplitudes. So this is the overall general formula, right? It's number of cosines plus a number of sines, a number of terms. A of n, which is the coefficient, which is the amplitude of the cosine signal, follows this formula, where n tells you the term number, because you have the first, the second, the third, and so on term. And B of n is the rule or the formula you use to calculate the coefficient of the sine terms, where n represents the term number. So basically you have a general term, and you just change the value of n, 1, 2, 3, all the way up to infinity to get the term specific value. And in order to get it, you have to integrate. You don't have to memorize this, it will be in the formula sheet, but you need to learn how to properly integrate.
So
Okay?
Bn for the sine and
Bn for the sine, an for the cosine. And then you have omega naught, which is the original function's frequency. And from that, you can calculate it if you know the period. T is the period of your original function. Here. And you'll notice all the frequencies are a multiplier of omega n times omega naught. So if n is 1, it will be omega naught, 2 omega naught, 3 omega naught, and so on. Clear? And that's why we call them harmonically related, because they have the same base frequency. Clear? Okay, so this is the Fourier series, which we've established. Now we can represent it in a different, now if you look at it, it's sine and cosine. We can represent it in other forms. One of them is the compact form, where you calculate A and B, but then you come up with C, which is the compact coefficient. So say C is the square root of A and B squared, and theta is tan inverse B over A. So you treat A and B as if they are a complex number parts of a real and a complex part. Another way is we know that sine and cosine can be represented by exponents using Euler's formula. So we can use the exponential form to represent the Fourier series. Regardless of the representation, we have to first calculate the coefficients of these sine and cosine harmonically related terms. Are we clear so far? Questions? Okay.
what's D and
D is this value. So to remind you, this is the formula that we're using, right? Cosine of an angle theta is equal to e power j theta plus e power minus j theta over 2, right? And sine theta is equal to e power j theta plus e power minus j theta over 2j. These are Euler's, these are trigonometric identities, Euler's formula. So since the cosine is exponentials and the sine is exponentials, you can mathematically actually represent the whole thing as an exponential. Clear? Which is this term over here. D is the coefficient of that exponential, which is equal to this formula over here, if you want to calculate it. Clear? Now, I don't want you to derive this formula. Don't even remember the derivation of it. Don't even memorize it. It's there. Just learn how to use it properly. Okay? So this is the series when the signal is periodic. For the aperiodic signal that is continuous, then we can use the transform. And do we remember Laplace transform? We studied at the beginning of the semester. A little shaky? Okay, no problem. We'll remember it today because Fourier transform and Laplace transform are very similar. They're very close. Even in the concept and in the application, they're somewhat close, okay? Let's see similarities. Laplace transform says that signals can exist in time domain and in Laplace frequency domain. Fourier says that they can exist in time domain and in frequency domain. It's the exact same thing. The only slight difference is that for Laplace, we use the term S, which is j omega. For Fourier, we just use the term omega directly, okay? Similarly, we have forward and inverse transform. So you have a pair. You have the signal x of t, and x of t has a representation x of omega. You remember that? Just to remind you a little bit more, we said that we have visual representation of signal in time, and we have a visual representation of signal in frequency. For example, this is sinusoidal waveform of frequency omega naught. This is a frequency omega naught. Magnitude is A, magnitude is A. Both of them give you the same exact information you need. What is the frequency? What is the amplitude? But one of them from a time perspective and one of them from a frequency perspective. And we all know that omega is equal to 2 pi over t. So they are very relevant. There is a relationship between them. Does that make sense? So the Fourier transform basically says, well, if I know the function as a function of time, x of t, I can easily represent it as a function of frequency, just to look at a different angle. Instead of looking at it from a time perspective, we can look at it from a frequency perspective using this formula, which you'll see a little bit also close to the Laplace formula. This is x of t, so I know x of t, I can find x of omega. And I can do the inverse process. I can know x of omega, and from that I can find x of t, correct? Why do I do that? Because sometimes a problem mathematically is complicated in time domain, but simple in frequency domain. For example, current and voltage relationship of a capacitor and of inductor in time domain is an integral equation or a differential equation, but in frequency domain, it's a linear equation, easier to solve. So the whole purpose of jumping from time domain to frequency domain is just to do less complicated calculations. Does that make sense? Are we clear, everyone? Up till this point, do we have a question? Good. Online, are we good? Okay, you know what follows this. An example. Okay. Here you have a graph of a signal. And it says find the Fourier transform of this rectangular pulse signal. First thing, are we going to use the Fourier series rules or the Fourier transform rules? If you didn't see the question, what should you go for? Series. But we said there are two rules we need for a function to be applicable to Fourier series. It has to be continuous. It has to be periodic. Is this signal periodic? Periodic يعني بتكرر شكل مكرر. Is it periodic? No, it's not periodic. If it's periodic, we would have plotted it at least. This is an aperiodic signal, which means which Fourier theory applies to it? The transform, right? So we need to use this set of rules, right? Which one of them? What do we know? What are we given? No, it says find the transform of x of t. What the shape shows? The graph. The graph represents which function? X of what? X of t. So you know what x of t is, and you need to find the transform, which means x of omega. So the unknown is actually x of omega, which means which equation do I use? First one, right? Okay, so what I'll do is just copy it. It says x of omega is equal to the integral between minus infinity to infinity x of t e power d what? Minus j omega t d omega, or dt. Thank you. Okay, dt. Now, we need to apply the rule, right? So first thing is we need to substitute the value of x of t. If I want to perform this integration, I need to know what is x of t. What is x of t from the graph? X of t is equal to what? What are these two values? Yes. Can you speak louder?
E minus t.
No, you've mentioned something, so I heard something. Okay, it's okay. Keep going. What is the value of x of t? This is the graph. X of t is equal to what? What are the two options? Tell me.
Is less than minus 2.
Which is equal to?
Equal to 0.
0. Okay, so I'm going to write the definition here. X of t is equal to 0 when t is less than minus tp over 2. What else?
From t is equal t is greater than 0 to tp over 2.
is equal to what?
Equal to A.
A. So you define this, you define this. Okay, and then what?
Minus T over 2 and T
Minus TP over 2 to
TB over 2.
also we're correcting this one, right? Okay, good progress. Then what? What happens after TP over 2?
Infinite.
It's equal to what?
Which one?
Yani so far, this defines this area. This defines this. What happens here? After TP over 2.
Infinite.
Is it infinity?
0.
The value of is 0. X of t is 0 when t is greater than TP over 2. Do you agree with that definition?
So that's 0, 0.
Can I, yeah, so 0, a 0, right? Or in other words, just to make it a little bit more simplified, we can say that x of t, okay, just give me a moment. We can say that x of t is equal to a, where t is greater than or equal minus TP over 2 and less than or equal to TP over 2 and is 0 elsewhere, right? If it's not within that range,
Only from the 0
only from minus TP over 2 to TP over 2, right?
it is this side. So only from the 0 to
No, you'll measure the whole. So what you did is you broke it into stages. You said from minus infinity to TP over 2. And then from TP over 2 negative to TP over 2 positive, and then they're right? Okay. So if I want to apply now, I've defined x of t here. What do I apply?
be equal to minus TB over 2.
So we'll say x of omega will be equal to, now I'll change the integration limits, right? Because from minus infinity to negative TP over 2, there's nothing to calculate. And then after TP over 2, there's nothing to calculate. So the new limit become, perfect. And in place of x of t, what do I place? A, perfect. And then we have, okay. So now we're done with the use of figure, with the signal analysis. From this point inwards, it's a purely mathematical problem. Integration is a problem. Do we remember integration rules?
Yes.
Good. So what is the integration of a e power j omega t with respect to t? Okay, let me remind you. A is a constant. Agreed? What? Integration rules? No. This module is signal processing, not math. So
Anything related to math?
you have the formula sheet in Moodle. Check it.
If we need to memorize all of that,
Remember, what you have to remember is this module has a prerequisite, which is math. You need to know math before you go to here. That's why I've put math support classes in the Moodle. But it's okay. We'll go through most of the rules that we will use. I will go through it, so it will refresh your memory, okay? A is a constant, right? We can leave it out of the integration. So x of omega is equal to a, the integration of minus TP over 2 to TP over 2 e power minus j omega t. The integral of exponential is what? The exponential itself. So e minus j omega t divided by j, j omega only. T is the variable because you're with a minus.
plus 1.
Plus constant is when you have an unlimited integral, but here we have integration limits, which means we're going to substitute them. An upper limit and a lower limit. Do we remember that?
Yes.
It rings a bell. Good. Where are we going to substitute the limits? Here, in place of this t, in place of our integration variable. So it becomes upper limit. Let's take all the constants out just to make our life a little bit easier, which are a and minus j omega. Here, upper limit is e power minus j omega. Instead of t, we put the upper limit, tp over 2, minus the lower limit, which is e power.
But if we will first take the jump minus TB over 4.
No, you start upper limit minus lower limit.
Like from the lowest to up.
Yes.
Okay, so it should be minus TB over.
This is minus, and this is positive.
I mean, we take it integrate minus TB over 2.
Yes.
So it should be minus JW minus TB over
No, you start with the upper limit,
upper.
not the lower. You start with the upper. Here it will be with the negative, so it will be minus j omega minus tp over 2. Okay? And then the minus and the minus makes it positive, right? And I'm going to take this minus expanded, يعني بوزع السالب داخل القوس, so this will become negative positive, right? Why did I do that? So I can have a over omega times positive term first, e power j omega tp over 2. And then this became minus e power minus j omega tp over 2 divided by j. What does that mean? Up to this point, is it clear?
I will take it, you take J beside.
This there used to be a minus here, right? We expanded it inside. So outside is positive, this is negative, this is positive. I just call the positive first, negative second, and this j is here, right? This part looks like what? Do we remember? ما غريبة صح؟ مرت علينا قبل شوية هنا e power x jx minus e power minus jx over 2j صح؟ sin x. فهير what do we have? What do we have? p2. حلو. من وين نجيب ال 2؟ Multiply and divide. Whenever you need a number to finish the rule, all you have to do is just simply multiply by 2, divide by 2, problem solved. This becomes sine omega tp over 2, right? Okay, let me add some space just to keep going. Yes, it is. 2a over omega. So what we ended up with is 2a over omega e power j omega tp over 2 minus e power minus omega tp over 2 over 2j. وصلنا هنا صح? It's this one. Just repeated it. This entire term is equal to what, قلنا? This one. This is equal to sine omega tp over 2. إلى هنا okay? Did we solve the question? What was the question? Find x of omega, right? طيب, can we find x of omega for any omega using this formula, regardless of the value of omega? What if omega is equal to 0? What will happen? DC signal, frequency 0. What do we have? This becomes a problem, right? الأوميجا اللي في المقام هتبقى مشكلة لأنه قسمة على صفر is an undefined value. You cannot calculate, but it should be defined. لأنه the question was define x of omega. So I need to get rid of this omega. Okay? I will do a mathematical manipulation so I can have a different format where omega is not in the denominator alone. What should I do? I'm going to use the rule of sinc. There is a function called the sinc function. S-I-N-C, sinc. Sinc x is equal to sine x divided by x. Okay? Sinc function, you might have seen it, but we didn't give it a name then when we were studying damping. It's basically a sinusoidal waveform that starts big and then starts to decrease. This is called a sinc. To remove the omega, to get rid of the omega, we are going to use the rule of the sinc. طيب. If I want to use sync, what is missing? يعني sync x is sine x divided by x. X here is what? Omega tp over 2. This is my x, right? It's a different color. This here is my x, correct? So I need this to be divided by omega tp over 2. This equation is a divided by omega. This 2 we can bring it down, omega over 2, right? Sine omega tp over 2. So what do I have missing to be able to represent this as a sync? What term is missing or what expression?
X.
TP, right? TP is the missing, this TP. So multiply by TP, divide by TP, solve your problems. This is a sync, right? Naida, let's start from the top. So far, are we good?
Yes.
Okay. Now I want to use the sync formula, this one, to get rid of omega. First thing, I'm going to rearrange what I have. I have A in the numerator. I have omega in the denominator. This 2 can be rewritten here لأنه مقام المقام بس صح؟ كنا جايبين بس لمقام المقام. And I have sine omega tp over 2, right? That's what I have. I need it to be in this form, sine x over x. What is x in my case? My omega tp over 2, right? I have omega over 2 in the denominator, صح? So what's missing from here to make it a sync? ايه الناقص عشان اقدر اعبر عنها كسync؟ الاوميجا يعني هي مفترض تكون sync omega tp over 2 is equal to what? Sine omega tp over 2 divided by omega tp over 2, right? Sine موجود, omega موجودة, التو موجودة. What is missing? TP. So let's multiply and divide by TP. When you do that, you can take this term and this term. This is the sync, right? So x of omega is equal to a TP sync omega TP over 2. Clear? Side sync. Forgive the handwriting. Let's enhance a little bit. A TP sync. Okay? Make sense? Which is what we have over here. This is, by the way, all the calculations, but in typed, because I know my handwriting is not very clear later. So this is what you end up with. And this is how you plot the sync. This is the magnitude, the highest peak of the sync. And then it starts to drop gradually. When it drops gradually, it follows the same as the sine. Clear?
That's it.
خلاص, this is your answer. Now you've defined it. Now you can calculate x of 0. X of omega equals 0 is when sync is equal to 0. Clear? واضحة الفكرة؟ So all I had to do, all of this is just math. احنا آخر جزئية كانت فيها الفورير كانت هنا. But it's math skills. That's why I need you to practice as much as you can with problems, because the exam is purely these problems. Question 4 in the exam, part A and B. A is Fourier series, B is Fourier transform. Clear? Question 4 is this question. So you need to practice. It might be a different type of signal, different shape, different design, but you have to learn the same formula and practice it. A or B, one of them. One is Fourier. Question 4 is Fourier, one series, one transform. So this week's lecture, next week's lecture are question 4 in the exam. Clear? Okay. Make it easy for me. فهمت انت اللي شرحناه اليوم؟ إذا فهمت أمورك طيبة خلاص. You follow. It's practice. والله ما من صالحنا كلنا, بس we have to follow the rules. So practice We have the problems, we have the tutorial problems, we have the past exam papers, we have the revisions. And I'm here until last day, until 17th morning. Your exam is at 10, right? Until 9:59, I'm there for you. Okay? طيب. So this is what we have. I think I've calculated it. خلاص. This is the Fourier transform. Now I want you to practice with another one, and then we'll see the properties. What about this function? Do you remember this function from lecture 2? Common functions. The unit impulse. When a unit impulse is a function which has only one value when time is equal to 0 and the value is equal to 1, right? So if I want to find the Fourier series for this function, or the Fourier transform, we can apply the formula. We can say delta of omega will be equal to the integral from minus infinity to infinity delta of t e power minus j omega t dt. This is the formula, right? Delta of t has only one value, which is 1, when t is 0, right? فإذا this integration only exists when t is equal to 0. Outside that, it's 0. So all I have to do is just direct substitution. It becomes 1 e power j omega times 0, because it only exists when t is 0. E power 0 is what? 1. So 1 times 1. So delta omega is equal to what? 1, which is what we have here. So you notice this is the time domain representation. This is the frequency domain representation type. If you compare, or if you look at this and the previous example, the time domain was a rectangle pulse, right? This was x of t. The Fourier transform, which was x of omega, was a sinc function. What do you notice about this? When the signal has limitations in time and it exists in a limited range, for example, here it's between t over 2 to minus t over 2 in a confined range, its frequency representation was spread, right? Same here, when it only existed at 0, at only one point in time, it existed in all points of frequency from minus infinity to infinity, right? This is one of the Fourier properties, which is called the inverse spread. Basically says if it's limited in one domain, it will be expanded in the other. This property should help you when you're doing calculations to know, is my calculations correct? If it cannot be confined in both domains, it cannot be limited in both domains. If it's limited in one domain, it will be expanded in the other. Clear? This is one of the properties. Now here we have some Fourier transform of common functions, similar to what we have in Laplace transform. So these are calculations pre-existing for some of the common functions, the exponential, the sinusoidal, the constants, and so on. Are we clear so far? Not really? Okay. This we have that in the formula sheet. Okay, now let's do the opposite process. Can you find, and let me just add some space to make it, yeah, just a moment. Okay, so just take a minute. We are good. Can you find the transform for this, the inverse transform? So it's the exact same shape, but this time the signal is x of omega. You know x of omega and you want to find x of t. Can we find x of omega from here? So this is the formula for x of omega. It's for the inverse transform. And we want to find x of t. Can we turn it off? Thank you. Can we do that? Can we do that? It's the exact same process. So where do I start with? Where do I start?
X S X.
Yes. So now you know this is x of omega. What is the first step?
So range.
Update the range. Okay. So we'll say x of t is equal to 1 over.
A
So what is my integration limits?
minus omega over 2 and 10 omega over
Okay. And then what? What is the value of x of omega?
2.
It's the same, a. Perfect. Then we have, do you notice the difference here? We're integrating with respect to omega, not with respect to t. So we'll need to pay attention to that when we're calculating. Okay, what do we do next? Said a can be, okay, so a over 2 pi integral from minus omega over 2 to omega over 2 e power j omega t with respect to omega. Then what? Let's integrate. What is the result of that integration?
A over 2 pi
A over 2 pi
E minus A W T
mm,
over
over what? Are we sure? The integrating variable is what? Omega, right? So when we divide by what? The integral of e power at with respect to t is equal to e power at divided by a. We're integrating with respect to omega, so we divide by what? So we divide by what? J what? Jt. Clear? In the previous example, we were integrating with respect to t, so we divided by omega. Now it's the opposite. Clear? You need to pay attention to that. It will make a complete difference in your answer if you integrate with the wrong variable. Okay, and then we have the integration limits, minus omega over 2, omega over 2. What do we end up with? A over, so 2 pi j t can all be considered constants. And then we can replace, we're actually replacing or substituting the upper and lower limit with this omega now, right? So the upper limit is e power j, the upper limit is omega over 2 t minus the lower limit e power minus j omega over 2 t, right? Can I extract a sign from this? Do I have all I need to use the sign? So to remind you the rule, sine x is equal to e power jx minus e power minus jx over 2j. They have all I need. So we have this. No, we don't need to change it, do we? See, there are some. So we have 2, we have j, right? So I have all we need. What is left here is a over pi t, and here we have sine, omega 2, the j goes, so omega over 2 t, right? Okay, so this is what? This is x of t. Are we done? Is this the final answer? When t is 0, we cannot calculate, right? If t is 0, we have a division by 0. So we need to get rid of that t in the denominator. So what would we do? What do we do to get rid of t? We'll go for sinc. Sinc x is equal to sine x over x. What do I need to make this happen? Hmm? حسب الدالة اللي بتجيك. والسؤال حيكون find the Fourier transform, but what is the shape of the function? It depends. It could be different. So you need to practice. Last bit, this one. ها؟ والله ربي يعينكم. Okay, what was your question? Where did you reach آخر point? Is this point clear؟ إلى هنا okay؟ طيب. So let's. The sign you didn't get where the sign came from, right? Okay, let's repeat it. طيب, we're using Euler's formula, okay, which is a rule that we can represent a sine function as an exponential combination. The rule is sine x is equal to e power jx minus e power minus jx over 2j. This is the rule, okay? So what I want to do is see if I can apply this rule here in this equation. Do I have all I need to substitute? So I have e power j omega over 2t minus e power minus j omega over 2t, right? Which represents this part, the numerator, right? And then I here have 2j, right? So I can rewrite this as, say, divided by 2j and just remove the 2 and j from here. It's still the same. صح? So I can take this entire term and say that, well, this term is the exact same as this. So it becomes what? It becomes x of t is equal to a over pi t times, now this becomes what? Sine what? right؟ لأنه ده الحد المضروب في الجي اللي هو مقابل x هنا. make sense؟ طيب هنا وصلنا إنه x of t is equal to this. طيب what if I ask you what is x of 0 if t is 0? What is x of 0? معناها هنعوض التي بزيرو صح؟ يبقى في قسمة على صفر ما حينفع صح؟ إذا this form is not suitable. ده من الإجابة غير الفورم ده غير منطقي لأنه ما ممكن نحسب به x of 0 so we have to change it. فلازم نطلع تي من المقام نتخلص منها بطريقة أو بأخرى. كيف نطلعها؟ هنستخدم قانون السينك. سينك x is equal to sine x over x, right? طيب عندنا sin omega 2 over t over 2 times t موجودة. What do I need? What is the missing term that I need to add in order to be able to extract sinc? Two what? طب what is x? What is the x that I need? This is x, right? Omega over 2t. طيب. أنا المحتاجة ليه يكون عندي sin omega over 2t divided by omega over 2t صح؟ I have the t part. يعني ممكن أقول over t وأمسح التي دي صح؟ t موجودة يبقى الناقص هو الأوميجا over 2 فنضرب في أوميجا over 2 أوميجا over 2 right؟ اللي هنا واضح؟ clear؟ Which is exactly what we did previously. Now this becomes, this is equal to sinc, right? And x of t is equal to a omega over 2 by sinc omega over 2 t. Clear? Good? Any questions so far? فنوت جست يعني الفكرة إنه ما بس نحل التكامل لازم نتأكد إنه المعادلة قابلة للاستخدام إنه ممكن أستخدمها وأحسب بها كل القيم المطلوبة. So if you stop here you get a partial correct answer but you need to get the full correct answer. So this is what we have which is exactly what you did. طيب what do you notice إذا قارنا المثال ده بالمثال قبله؟ لما x of t كانت rectangular pulse x of omega كانت sinc function صح؟ والعكس لما كان x of omega sinc x of t كان rectangular. And this is one of the properties of the Fourier transform اللي هي اسمها ايه؟ time frequency duality. بمعنى انه السيجنال او الفانكشن exist in a pair. Okay? الشيب pair الريكتانجولار pulse البير بتاعه السينك. فبغض النظر which domain you're at, the other pair will have that look. If it's rectangular time domain, it will be sync in frequency domain. If it's sync in in time domain, it will be rectangular frequency domain and so on. And this is another property that you can use if you don't want to do calculations. And you already know what the shape of the function will be. Clear? اللي هنا واضح؟ So far we did two properties. We did time frequency duality. Low shape is a pair. The function exists as a pair of shapes. Regardless of what domain you're looking at, you can flip it. And then we had the inverse spreading properties. Then we have more properties. And if you look at these, you'll see that these are identical to the Laplace transform properties. And these should help you with reduced calculations if needed. Number one is time shifting. Now remember, احنا بنبدأ بنفس البير. يعني إذا عندنا original function x of t, أكيد عندها Fourier transform x of omega. So if I know the original pair x of t with the Fourier transform x of omega, for example, from this table, مثلا, we have this table of common functions. You know x of t and you know the corresponding x of omega. If you do a time shift بمعنى فقط استبدلنا t minus t0, okay? بدل ما الدالة تبدأ في صفر مثلا تبدأ at point 2 or at point negative 2, this is called a time shift. We don't have to do further calculation. A shift in time is equivalent to a multiplication by an exponential in frequency. يعني نفس الأوميجا الأصلية will just multiply it by an exponential term. e power j omega t naught, where t naught is the value of the shift. Clear? We have the exact opposite to that, which is the frequency shift. اللي هي ال shift in frequency is equivalent to multiplication by an exponential in time. Clear? So far we good? We have the time reversal property. If x of t and x of omega is a pair, x of negative t will be equal to, will have the Fourier transform x of negative omega. And if you add the negative sign here, you'll add a negative sign here, simply. And finally, we have the time scaling property. And this property is identical to the Laplace time scaling property. If you multiply time by a factor, which means يعني, either you expand the signal or compress it in time, this means you will divide by that factor in omega. It will be omega over a, and then you'll divide the entire representation by the factor. Clear? So these are just some of the properties. And the whole purpose of these is, I don't want you to derive them or prove them or anything. Sometimes they help with calculation. So you don't have to calculate. So for example, this one. You already know that this is TP over 2 to TP over 2, and this is the function. What if I shrink it? So it becomes minus TP over 4 to TP over 4. This is time scaling, right? I multiplied by half. I don't have to change anything here except what? If you go to the time scaling, divide omega by the half. So it becomes A TP. Oh, let me use a different space just to give myself some. It becomes A TP sync. Here, instead of omega, I would put omega over half, TP over 2. And then I'll divide the whole thing by 1 over 2. Make sense? Which is exactly this property. Replace every omega by omega over the factor and multiply by 1 over the factor. So I don't have to do the whole calculation and calculating the sign and the thing. You don't have to do that. Just substitute for the values you know, based on the factor that you have. Clear? Any questions? Any concerns? Online, are we good? Okay, so with that, let me come again. ما بس ايه؟
ما بس من اليوم دكتورة.
لا خلاص خلصت معكم انا. وقف. Let me just stop the recording. Okay.